Okay guys, so we're finally on to finding zeros of polynomial functions, and so we're going to do a couple problems. I'll do a couple with you, and then I'll have you guys probably do some by yourself. Up here at the top just is kind of a list of a couple things to consider when you're trying to find the zeros. If you can, you always want to try factoring first. That tends to be one of the more efficient methods, but oftentimes, especially when my degree is bigger than 2, if it's to the third power fourth or bigger than that, sometimes factoring isn't that easy to do from the beginning. And so what we can do is we can find all of our possible zeros using the rational zero theorem, which I'll get to in a little bit. And then from there, we'll use the factor theorem to determine which of those possible zeros actually are zeros for the function that we have. So if we jump in with number 11, we're going to try to find all the zeros. Because this is x to the fourth power, I know this is going to have a total of 4 zeros. Some of them might not be real, but we will have 4. So let's take a look. I don't think I can factor this right now. So what I want to actually do is find the list of all of my possible zeros, or my possible rational zeros, and I can use that with my rational zero theorem. Now, let's see what the rational zero theorem has to say. If f of x is a polynomial function with a degree greater than or equal to 1 with integer coefficients, then every rational zero of the function comes in the form of p over q. Let's figure out what p. P are all the integer factors of the constant term, and q are all of the integer factors of the leading coefficient. Now, one thing I'll point out is when we look at factors, we're going to take both the positive and the negative versions of those factors. So if we look at number 11, let's start by identifying all of our factors of the constant term. Well, that's going to come from this. And if I want to find all the possible factors, well, let's just see what divides into 30. So 1 goes in, 2 goes in, 3, 5, 6, 10, 12, oh, not 12, I don't know what I'm thinking, 15. And really, guys, what I just do is I start at 1 and just start seeing what works. So 1, 2, 3 worked, 4 didn't divide in, 7, 8, 9 didn't divide in, 11 doesn't, 12 doesn't, 13, 14, 15 does. And then once you're at the halfway point, normally the last one is just going to be the value itself, which is 30. So that's all of my possible, or that's all my factors of my constant term. Now I'm going to look for all of the factors of my leading coefficient. Well, this is nice and easy because my leading coefficient is just 1. So all here is 1. Well, if I want my list of all of my possible rational zeros, then I'm going to take all of the pairs of p over q's. Well, here's all my p terms. Luckily, in this case, I only have one q term. So all of my possible rational zeros come in this form. So plus or minus 1 divided by 1, 2 divided by 1, 3 divided by 1, 5, 6, and I'm just going to list those out. If I also had a factor here of 2, I would then do 1 divided by 2, 2 divided by 2, 3 divided by 2. Anything that was already here we don't write again, but anything that's new we can add to our list. So what I have now is a list of all of the possible rational zeros for this. And by rational, we just mean things that can be written in a fraction form. So at this point, we just have to start testing. And we're going to use the factor theorem from before, which tells us that if something's a factor, then its remainder, when we divide it in, will be 0. I normally like to start with smaller values. So I'm going to just start with 1 and see if that works. So I'm going to take, so in this case, my 0 would be 1. My factor would be x minus 1. I'm going to divide it into this. Okay, so drop the 1, multiply by 1, I add, I multiply by 1, I add, I multiply by 1, I add, I multiply by 1, and you'll notice that my remainder is negative 24. So that's pretty clear that 1 is not actually one of my zeros because the remainder was not 0. So now I try something else. I often will try negative 1 next. I'm going to try 2 next instead. So I'm going to go back to this. My coefficients were 1, 3, negative 7, 9, and 30. Drop the 1, multiply by 2, add, multiply by 2, add, multiply, add. Whoopsie, sorry guys, this is supposed to be negative. I just copied that wrong. So multiply by 2. And when I add those, I notice that I get a remainder of 0. So that means that 2 is in fact one of my zeros, or in other words, I have a factor of x minus 2. Well, my goal isn't just to find 1, I need to find all of the zeros. So from this point, I actually have 2 options on what to do next. Option number 1 is to keep doing synthetic division, and I would do it from this point. And I'm actually going to do that first, but then I will show you the second way we could do this instead. I've done this problem already, so I happen to magically know that -5 is going to be one of my other zeros, but if you didn't know that, you would just have to keep testing ones until it worked. When we test another value, don't go back to the original coefficients. Start with the leftovers from this synthetic division problem, because now I have this simpler. This was an x to the 4th. If I were actually to write this out, this represents the polynomial 1x cubed plus 5x squared plus 3x plus 15. And I want to take it out of that simpler polynomial to see what I have left at the end. So let me do some synthetic division. I drop the 1, multiply by -5. Add, multiply by -5, add, multiply by -5, and you'll notice that I get a remainder of 0 again. So if I look at it this way, I know that I had I had a 0 of 2, so in other words, I had this factor. I had a 0 of this, so in other words, I had this factor, and this tells me what I have left. Because I went from the simpler version here, which is the equivalent of an x cubed polynomial, I'm left with an x squared polynomial. So I have x squared plus 0x plus 3. Now, before I dig into this, I did mention a little bit earlier that there was a second way to move forward from here. Well, we said we know that what I have in here really represents the polynomial x cubed plus 5x squared, it's plus 15. And if you prefer, you might have noticed that this is actually something that we can factor by grouping. These terms both have an x squared that I can factor out. These terms both have a 3 that I can factor out, which leaves me with x squared plus 3 times the factor x plus 5. And when we did that, you'll notice I end up with the same factors. This gave me a 0 of -5. This is my leftover stuff. And then, of course, we had this term, this 0 up here that had already been taken out by this point. So that's just another option. Once you get to the cubic, sometimes you can factor by grouping at that point. Well, we're almost done with this problem. It didn't ask us to factor it completely. It asked for all of the zeros. So you'll notice at this point, I know that I have a 0 of 2, a 0 of -5. Let's figure out what the zeros are of this. Well, I just want to say, what makes this 0? Well, if I subtract 3 onto the other side, take the square root of both sides, make sure you put that plus or minus, I'm left with this here from Algebra 2, and maybe even Algebra 1, that the square root of a negative number, well, the square root of negative of 1 is I, so I can actually rewrite that square root of -1 becomes I, and then I still have a 3 left over on the inside. Okay, so if I actually want the list of my zeros, I have 2, -5, and plus or minus root 3i. When you write this, make sure that I is clearly a radical sign. We've taken out that square root of -1. It's multiplied by root 3. It's not under the radical sign. Okay. So we just did this problem together. I'm going to have you guys do number 12 by yourself, but I actually don't like this problem. When I went through and did it, it's fairly special. So go ahead and get rid of that for me. Instead, what I'd like you to please do is this problem. Okay. The first thing that you should do is find a list of all of your possible rational zeros. Okay. Start there by testing values, but I want you to find all of the zeros. Notice this is an x to the 4th, so you have 4 zeros. So this is a problem I want you guys to do by yourself. I'm also going to have you do number 13 by yourself. You'll notice this is a quadratic, so try factoring. If you can't factor it, use the quadratic formula, but that's something hopefully you guys can do, and I'll put up answers for you to check when you're done. I want to do number 14 with you because this is something just a little bit different that we can actually factor. So I know this is an x to the 4th term, but if we can rewrite something to look like a quadratic, often factoring will become an option. You'll notice that I have only odd degrees here and then a constant. So I have x to the 4th. Oh, I said odd. I'm sorry, I meant even. I have x to the 4th, x squared. I'm going to rewrite this kind of like we did with trig to represent this as something squared. Well, x to the 4th is really x squared squared. This I can then write as 6 times x squared minus 27. Well, if you think back to trig when we had like sine squared, sometimes we represented that sine thing with y. So if you think about this, I really have something squared plus 6 times that something minus 27. And you can see that that's in a quadratic form. That's something I can hopefully factor, if not synthetic, or I can use the quadratic formula. But in this case, I can factor it. So let's see if we can find two things that multiply to negative 27 but add to a positive 6. Well, 1 and 27 multiply to 27 but don't add to 6. 3 and 9 could possibly get to 6. Let's see if we can play with that. Remember, instead of x, I have x squareds here. So we said 9 and 3. Well, if we're going to do that, I'm going to need a positive 9 and a negative 3, so that these multiply to negative 27 but add to a positive 6. Well, I'm not done at this point. These aren't my zeros. We're just in the process of factoring. So I'm going to find the zeros of this. I'm going to add 3 to both sides, and then take the square root of both sides and make sure I put my plus or minus. Notice that this thing here gave me 2 zeros. Okay, now let's go here. I'm going to set this equal to 0. I'm going to take the square root of both sides. Notice again I have the square root of negative 9. Well, I didn't really write this out earlier, but really what I have here is the square root of negative 1 times the square root of 9. Okay? Well, I can rewrite this as plus or minus. This is I. Well, root 9 is 3. Okay? This was an x to the 4th. It should have 4 zeros, and you'll notice we end up with 1, 2, 3, 4 zeros. Okay? So make sure either you guys could have paused earlier to do 12 and 13, or you can do those now. But I need you guys to finish those problems for me, please.